Welcome, first-year biomedical engineering students. I'm absolutely thrilled to have you here today. In this explainer, we're embarking on a fascinating journey into the very foundation of how electrical circuits are built. Whether you're aiming to design advanced medical imaging devices or life-saving patient monitors, your journey starts right here with the fundamental flow of electricity.
Here's the roadmap for today's explainer: the one-bulb mystery, understanding series circuits, understanding parallel circuits, series versus parallel, and finally, busting circuit misconceptions. I promise you this, we're going to build your physical intuition about how electricity actually behaves before we ever introduce a complex equation.
Section 1. The one-bulb mystery. Let's dive right into this with a scenario you've almost certainly experienced yourself.
Picture those old decorative string lights. You plug them in, and one single burned-out bulb causes the entire string of 50 lights to just go completely dark. It's incredibly frustrating, right? But then, think about the standard wiring in your home or in a hospital room. If one light bulb burns out in the ceiling, the other lights in the room stay on and your appliances keep humming along perfectly. Why does the exact same event, a broken bulb, cause two completely different electrical outcomes? Well, to solve this mystery, we first need to remember a fundamental law of physics. Electric current is, at its core, simply the flow of electrons. But for those electrons to actually flow from the positive terminal of a battery to the negative terminal, they absolutely require a complete, continuous, closed path. We call this an electrical circuit. If that path is broken or opened at any point, the flow of electrons stops instantly. It's literally all or nothing. So knowing that we always need a closed loop, it raises a really crucial question for us as future engineers. Should we always connect electronic components in the exact same way? As you might guess from our light bulb mystery, the answer is a resounding no. How we actually arrange our components drastically changes the behavior of the entire system.
Section 2. Understanding series circuits.
In a series circuit, components, like resistors or light bulbs, are connected end to end. We call it series because the current passes through components sequentially, in a continuous series of events, kind of like binge-watching episodes of a TV series, one right after the other. It forms one single path. Intuitively, think of it like people standing in a single-file queue, or cars driving on a one-lane road with absolutely no exits. The electrons leave the battery, travel through resistor 1, then resistor 2, then resistor 3, and finally back to the battery. There is literally nowhere else for them to go.
I really love this analogy from our source material to help build that physical intuition. It notes that free electrons flow through conductors like marbles in a tube. If you push one marble into a completely full tube, one marble pops out the other side. Because there's only one single path in a series circuit, the rate of flow, which we call current, must be exactly the same at any specific point in time. The current doesn't get used up as it goes around. It flows at a constant, steady rate everywhere in that loop.
So the crucial takeaway here is this. In a series circuit, you have one path, and the current is uniform everywhere. But what about the voltage? Well, the total supply voltage from the battery is actually divided or shared among the components. As the current pushes through each resistor, there's a voltage drop. And here's the critical vulnerability, the exact answer to the first part of our mystery. If one component fails, the tube is blocked, that continuous path is broken, and the entire circuit immediately stops working.
So how do we analyze this mathematically? Honestly, it's remarkably simple once you grasp the physics. If you force electrons to flow through multiple resistors in a single line, you're obviously increasing the total friction, or the overall difficulty for that current to flow. Therefore, to find the total equivalent resistance of a series circuit, you simply add the individual resistances together. R total equals R1 plus R2 plus R3. The more components you stack in series, the harder it is for current to flow, and the higher your total resistance climbs. Section 3. Understanding parallel circuits. Because what if we don't want our entire system to shut down just because one single component fails?
Here, instead of a single continuous chain, all components are connected between the exact same set of electrically common points. We call it parallel because the electrical branches run side by side without intersecting, very much like parallel geometric lines. This gives us multiple, completely independent paths for the current to take.
To build your physical intuition for this one, I want you to think of water flowing from a large main pipe that suddenly splits into several different pipes simultaneously, all leading to the exact same final destination. The total amount of water divides and takes those different paths. In a parallel circuit, the total electrical current behaves the exact same way. It divides among these various branches based on exactly how much resistance each branch has. Because every single branch connects directly across the same power source, every branch feels the exact same electrical pressure. Therefore, the voltage is exactly the same across every single component in parallel. And because the branches are independent, if one pathway gets blocked, say a light bulb burns out, the electrons just continue flowing down the other available paths. The rest of the circuit keeps working perfectly. And there it is. That's the answer to the second half of our light bulb mystery.
Now, let's tackle the mathematics for parallel equivalent resistance. I know, this fraction equation looks a bit strange and maybe a little intimidating at first glance. 1 over R total equals 1 over R1 plus 1 over R2, and so on. Why on earth doesn't it just add up nicely like a series circuit?
It all comes down to first principles. In a parallel circuit, the total resistance is actually always less than the resistance of the smallest individual resistor. Why? Because every single time you add a new parallel branch, you're opening up a brand new path for the electrons to travel down. Even if that new path has a lot of resistance, it's still an extra road, and more roads mean it is generally easier for the total traffic to flow. So mathematically, adding individual resistances in parallel actually diminishes the total equivalent resistance. Let's solve a really simple conceptual example. If you have two 10-ohm resistors in parallel, intuitively, having two identical paths makes it exactly twice as easy for current to flow. Therefore, your total resistance drops right in half, to just 5 ohms. See? No complex calculator needed, just pure physical intuition.
Section 4. Series versus parallel. Let's synthesize everything we've learned and view these two concepts side by side.
When we compare them directly, we see exactly how the physical structure dictates the electrical behavior. In a series circuit, you have one single path, so the current is identical everywhere, but the voltage divides. If a break happens, everything fails. In a parallel circuit, it's the exact opposite. You have multiple paths. The voltage is identical across every branch, but the total current divides among them. And crucially, if one branch fails, the others soldier on completely uninterrupted. If you truly understand these structural rules, you don't need to blindly memorize formulas. The behavior of the circuit just makes logical sense.
Section 5. Busting circuit misconceptions. Before we wrap up, it's time to put on my careful professor hat.
Let's bust 3 massive myths that students often bring into the lab. Myth 1. Students think current is always the same everywhere. The reality? It's only the same in a series circuit. In a parallel circuit, it divides. Myth 2. Students assume voltage is always divided equally in series. The reality is that voltage is shared in proportion to resistance. A bigger resistor demands a bigger voltage drop. And myth 3. Adding more resistors always increases total resistance. The reality? Adding resistors in parallel actually lowers your total resistance by adding more paths.
Let's bring all of this theory back to the real world, especially for you as future biomedical engineers. Simple devices like flashlights use series circuits, but a crucial medical application of series circuits is the protective fuse inside medical power supplies. If a device draws way too much current, the fuse intentionally burns out, breaking that single path and protecting both the expensive machinery and, most importantly, the patient. Parallel circuits, on the other hand, are the absolute backbone of hospital electrical systems. When you plug in a patient's ECG system, an infusion pump, and a patient monitor, they are all wired in parallel. They all require the exact same stable voltage. And critically, if the infusion pump fails or gets unplugged, the patient's ECG system and monitor must keep running flawlessly on their own independent branches.
So, we've mastered the basics of pure series and pure parallel circuits today. But real-world medical devices aren't usually this simple. What happens when you open up a complex patient monitor and find resistors connected in both series and parallel within the exact same circuit? How do engineers analyze that? Well, that is a fantastic puzzle, and it leads us directly into our next lesson on Kirchhoff's laws. You definitely won't want to miss it.